So today we want to look on the combinatorics of free probability theory. And I mean, last time we have seen combinatorics emerging in central limit or limit theorems, and we saw that it seems to be a good idea to write moments in terms of other quantities, which we call kappas, and which will be called cumulants, or precisely free cumulants. And this connection between moments and cumulants is given by summing over non-crossing partitions in free case. And maybe if you have multivariables, we also saw that we have to respect a constraint, which means that we are summing only over those which in some sense are smaller than the kernel of the indices determining which joint moment we consider. Okay, and today we want to make this more rigorous and precise. So this is the chapter on combinatorics of free probability theory. Free probability theory, and so we will talk about more precisely about non-crossing partitions. In particular, they have more structure. They are poset, they are lattice. And we are looking on specific functions on them, multiplicative functions on non-crossing partitions, and the goal is really to define those quantities kappas and free cumulants, but in the most possible general. So the real goal is to define and understand the free cumulants, which are alternative way of talking about moments, but cumulants reveal much better the structure of freeness. Okay, and so let us start right away. Is trying to understand the structure of this formula of relating moments and cumulants. So this was a sum over non-crossing partitions, and essentially what we are using there is that non-crossing partitions form a poset, that we have an order there, partial order. So maybe find this. So if I have two non-crossing partitions, here in sigma, non-crossing partitions of n elements, then we say that one is smaller than the other. And we write this in the usual less or equal sign way. So here is less or equal than sigma. If we get pi from refining pi, which means we decompose some blocks of sigma into smaller blocks. Or the other way around, every block here should be contained in one block here. Okay, so this means if block of smaller one, of pi, is completely contained in one block of sigma. It's completely contained in one of the blocks of sigma. Okay, and so this gives us a partial order on non-crossing partitions, and a set with a partial order is usually called a poset. This stands for a partially ordered set. And this is only a partial order. Partial order means we cannot compare any two elements. We can only compare some of them. So this is a partial order. Smaller than the second element, and the second is smaller than the third one. Of course, then you also have the first is smaller than the third one. Okay, but it's not true that if I have x and y, then I can always compare them. Okay, and so so I write here less or equal, and if I only write less, then we understand this in the usual way that it means less or equal, but not equal. So we also use notation. Pi is less than sigma, so this means strictly less than sigma. So this by definition should mean pi is less or equal than sigma, but it's not equal. Okay, this is just Good. Okay, and then, I mean, later we will see that actually this poset has more structure. It's a lattice, but for the moment, let us just observe that this in particular means there is one largest element and one smallest element. So there is one element which is bigger than every element in my poset, and there is one which is the smallest one. Okay, the largest one, of course, is the one which only has one block. And the smallest one is the one which has as many blocks as possible, so namely where each block is just a single. So there's a maximum element, NCN. And of course, at the moment we are fixing n. We are only comparing elements which are partitions of the same number of elements. Of course, I mean, later on n will also vary, but the poset here is for fixed n. For fixed n, there is a maximum element. Maximum element of NCN. And maximum means it's an element which is larger than any other element in the poset. Of course, also larger than itself. Okay, so this is the one which has only one block, and usually I write this as 1n. Okay, so the n denotes the n here, and 1 denotes it's the largest one. And this is of course the partition which has only one block which contains two elements. 1 up to n. So this is this biggest block. And there is a minimal element which has only singles as well. And of course, I really want this by 0. Minimal element SCN. So this is denoted by 0n. This is the partition which has n blocks, and each block consists only of one element. So there's a block which contains 1, there's a block which contains 2, and so on. And the last block only contains n. And so, graphical terms, it's just this partition. Good. Okay, and later on we will see that actually, I mean, we have a lattice structure, which means that for any two elements there is a unique maximum and a minimum. So, but for the moment, we just look on the poset structure. Good. Okay, so maybe let me make an example. Examples of this order. So for example, if I have one partition of 8 elements, then we have, for example, let me consider the following. Non-crossing partitions, so 8 elements, 1, 2, 3, 4, 5, 6, 7, 8. Let's take the partition which has a block 4, 5, maybe a block 2, and then a big block 1, 3, 6, 7, 8. Okay, and now if I want to find a smaller element, this means I should decompose some of the blocks into smaller blocks. For example, I have here a big block, so let us decompose this into smaller ones. So I'm keeping this one and this one, but this big block I'm decomposing into, let's say, 3 blocks like this. Okay, so this partition here is, so if this is phi and this is sigma, then the sigma is less or equal than pi. And of course I could also decompose this into smaller blocks. So this means, every block of the smaller one, or the other way around maybe, let's say every block of the bigger one is a union of some blocks of the smaller ones. So I'm getting the smaller one by refinement of block structure. Okay, and this means, of course, there are situations where it's not true that, I mean, sigma is less or equal than pi, or the other way around, because there are blocks which are neither contained in the blocks of the other one. So this means this is really just a partial order. So this here is only partial order, which means I cannot compare any pair of elements with each other. Let us, for example, look into non-crossing partitions of 3 elements. Maybe let us look how the elements are sitting there, how to compare them. of course, there I have the biggest element, the maximum, 1, 3, and I have the smallest element, and then I have 3 other elements, which are of course smaller than this one and bigger than this one, but which cannot be compared to each other. I mean, that's the ones which have one singleton and a block of size 2, and of course, I mean, those guys are all smaller than this one, they are bigger than this one, but among themselves I cannot compare them, because I mean this is not bigger than this one, because I mean this block here is not contained in the block here. And also the other way around, this block, 2 block, is not contained in any block here. So those 3 cannot be compared to each other. Those elements means it's only a partial error. Good. Okay. And now, so we have those non-crossing partitions, and now we want to look at our functions. Now, this relation between moments and cumulants, which was given by summing over elements in non-crossing partitions, so in our poset. And so actually, what we have are now functions on our poset. And we have 2 functions which are related. Okay, and this is captured into a very general structure, which is called the incidence algebra or poset. So we are only interested in the non-crossing partitions, but this can be put in a much more general context of posets. And in particular, the classical theory, where we are dealing with all partitions, works in the same way. So let me define this general structure. What we have is a kind of convolution of such functions. The structure which we have around the summing over all non-crossing partitions is like doing a convolution of such functions. And so I mean this definition, this very general setting goes back to Giancarlo Rota, famous combinatorist, from 1964, and essentially it's making a very general frame out of many things which have been around before. Okay, so this gives a very general frame and somehow also uniform theory of combinatorics for many things. Okay, so this is in the setting of a poset, a finite poset. Okay, so usually, of course, non-crossing partitions are only finite number, so we are looking on finite posets. We could also look on locally finite posets, but we are not needing this. Okay, so let just P be any finite poset. So B be finite poset. Okay, and then we consider functions. And actually, in the most general case, it's good to consider functions of 2 variables. And we are only interested in functions of the 2 variables if the first variable is less than or equal to the second one. And those functions we denote by P. P is a superscript 2. P2, those are the pairs we are considering. And then the functions are on this set. So we're looking on pairs of elements in our poset, sigma, in our poset, but we want that pi is less or equal than sigma. Okay, so we look at functions, but which somehow respect the structure. Okay, and so now we define functions on this thing, which means functions taking on values of 2 variables, but only values if the first variable is less or equal than the second variable. So we define functions. Consider functions, and then for 2 such functions we define a convolution. So let's say consider 2 functions fg, which are functions on this P2, functions going to C. That's the type of functions we will later consider. So we have functions on our poset and they take on values, complex numbers, and those numbers are the moments, or maybe for other functions, the cumulants of all variables. Yeah, so if I have two such functions, then we define a convolution which gives another function of the same type. So for such functions, define a convolution which we denote by f star g. This will again be a function from P2 to C, and the definition is the following. This by the following, so then we say f star g. So this should be a function of two variables. So let's say p and sigma. And this should of course be defined somehow f g. What we are doing is, so what you should think of, I mean pi sigma, pi is less or equal to sigma, so you should think of this as somehow interval from pi to sigma. Okay, and then in the definition we are splitting this interval into two subintervals, the beginning and the end. So this means we are summing over all possibilities. So we are summing over all tau in our poset, which are greater or equal than pi and less or equal than sigma. So we are summing over all elements which are lying in the interval from pi to sigma, and then we take f, essentially applied to the beginning of this interval, so this means f of pi and tau. And you see, tau is greater or equal to pi, so f is defined there. And then we multiply this with g of the second part of this interval, from tau to sigma. Okay, so that's our general definition. And maybe in the context of moments and cumulants, I mean, it looks as we didn't have function of two variables, so what we have there is essentially a one variable version of this. So we have functions which only depend on one variable. So we also have a one variable version of this. Namely, we can take the convolution of a function of one variable with a function of two variables. A priori, it's not clear how to do it if I want the convolution of two functions of one variable. In our case, usually one function will have two variables and the other one will have one variable, and this can be the moments of the cumulant. Okay, so this means we consider also a one variable version of this. Okay. This means I have now in my convolution one of the two functions is a function of one variable, but the second is still a function of two variables. So I consider f, which is just a function of one variable. So this is just defined on my poset. Okay, it's not complex numbers. But I also have another function, let's say g, which is defined on two variables. Okay, and then for this, we define also the convolution. Define f star g, and the result is now again a function of one variable. So this is the function p c, and the definition is essentially like this by just omitting the first variable in the first formula. Okay, so f star g. So this should be a function of one variable. So let's say f sigma. This is defined, and now we are summing over tau in our poset, which are just smaller or equal to sigma. So tau is less or equal than sigma. Okay, and then I take f of tau, and for the second variable I take as before g of tau, sigma. Okay, so this is definition, but okay, so we would like to make this connection with moments and cumulants, where we essentially connecting functions. This will be like a moment or cumulant function, but the question is what should this g be? Up to now we haven't seen things like this, and this is a function which tells us what we should do sum. Okay, and there are specific functions which we are choosing. So namely, there are in particular the delta function. So there's a unit element for our convolution. And then there's also the theta function, which tells us that we should sum over everything. And that's what we were doing by having this connection between moments and qubits. Okay, so there are special functions of two variables, special functions. And one of them is just unit elements. I mean, we have here a convolution. Okay, and so of course the question is there an identity element for this? And this of course is given by a function which is called the delta function. And then there's also a function which is called the theta function. So this here is theta. This here is delta. And they are both functions from two variables. And they are given by the delta function, of course, is what the name says. It's delta function, so it's something of two arguments. And delta means it's only one if the two arguments are the same, otherwise it's equal to 0. Also delta of sigma, so this is 1 or 0, and it's 1 if this is equal to this, so if pi is equal to sigma. And it is 0 otherwise, and this means if pi is less than sigma. Because those functions are only defined if pi is less or equal to sigma. Good. And the other function, the theta function, is the function which is 1 everywhere. So for every pair where the first element is less or equal, then the second it is equal to 1. Theta function, maybe we can write it here. Theta of pi sigma is always 1 for all possibilities which are allowed, and these are the pi's which are less or equal than sigma. Good. Okay, so let me make a few remarks. Or maybe this relation of the convolution formulas for one variable and two variable function, of course, is somehow the same. And if you're looking here in this summation, I mean, we don't have a lower argument here, but I mean, if you're choosing the minimal element here, then this corresponds to pi there. So if you have a one variable function, you could think of this, or you should think of this, as being a two-variable function, but the first argument is just the minimal element 0. And then those formulas fit together. So we should think of f, little f, which is our one-variable function, as a restriction of the corresponding two-variable function, capital F. And the relation, of course, is little f of sigma is the same as capital F from the 0 element to sigma. And I mean, if you then use the convolution formula for this capital F, this gives you exactly the formula for this. Because then I mean pi is 0, and then this capital F will be this little f, and of course in the summation here, if pi is the 0 element, then this is no constraint at all, because I mean 0 is less or equal than anything. So this doesn't give any additional condition on Good. Okay, and then as I said before, essentially those functions of two variables, you should think of them as actually being a function which depends on the interval between the two variables. Because I mean you're also summing here over this interval. That's the information which is needed of this function. So think of our two variable functions as actually functions of intervals interval in the poset, of course, I mean, if I say interval from pi to sigma, this should be all the elements which are greater or equal than pi and less or equal than sigma. This is by definition all the taus such that pi is less or equal than tau, and tau is less or equal than sigma. And of course, I only have an interval of two guys if the second element is greater or equal than the first one. And that's exactly the condition which I have in my functions. I only evaluate them or define them on situations where pi is less or equal than sigma. And then I have an interval here, and this interval, of course, is not empty, because it contains at least pi and sigma, which of course might be the same. Good. Okay, and then with this, you see in the definition, as I said before, so what I'm doing here is I take the interval from pi to sigma. I'm taking the interval, let's say, from pi to sigma. Of course, in the general poset, this is not necessarily a linear structure like this, but anyhow. And then I'm summing over all powers in between, and I'm decompose the whole interval into these two subintervals, and I apply f to the first part and g to the second part. So this means the definition of convolution f convolved with g, the sum over all decompositions of the interval by sigma. So if I want to calculate the value on this interval of the convolved thing, we sum over all decompositions of this interval into two subintervals. Into the two subintervals. Beginning of this interval from pi to tau, and the end of this interval from tau to sigma. Good. Okay, now of course we have this convolution, and of course this convolution really behaves like, the convolution is a kind of multiplication. So it behaves like a multiplication, so it should be particularly associative, but you can also ask the question, does it have a unit? If there a unit, which means convolved with this unit, I get the same result. And there is one, and clearly this is the delta function. That's the relevance of this delta function. It's the one for this kind of convolution. Delta function delta is clearly the unit of the convolution. So this means if I convolve function f with delta, then I get f, and I can do it in any order. So delta convolved with f is also so like this, because let's say g is a delta function, then I mean g is only 1 if tau is equal to sigma, because that's the definition of the delta function. The first variable must be equal to the same. So in this sum, I'm actually only summing over one argument, over one tau, which is sigma, and then I have here f pi and sigma. So you see, I mean, that I get exactly f star delta is just f. The other way around, the same. Good, so this is the unit. And then, one should also check that this is really an associative operation. So, just have to write down from this yourself that this really is a kind of multiplication. Delta star is associative. So if I have three functions, I can convolve them in various orders. So if I have f, g, and h, I can first convert f is g, and then the result is h. The result is again a two-variable function. But I can also first convolve g with h, and then the result is f. You should check that this is the same. So this is associative, but you should also see that in general there's no reason that it is commutative. So I really have to keep the order. Because I mean, the value on the beginning of the interval and the value on the end of the interval might be different for functions. So there's no way of getting that f convolved with g is the same as g convolved with f in general, the general process. Of course, in special situations it might be the case. In general, it's not good. Okay, but so what we have here is now essentially we have a multiplication. So we have a function. We have our function of two variables for which we define a kind of multiplication, which is convolution. And of course, for functions, there's also usually a linear structure. It's usually very easy. If you're going to C, you can take the pointwise addition. So we can also equip those functions of two variables with the pointwise addition, and then we have a convolution. And this structure together is usually called the incidence algebra of P of our poset. So what we have here is the incidence algebra of our poset. So this means functions of two variables of our poset equipped with the addition for the functions, pointwise addition, but then the convolution as the multiplication. And this convolution is the crucial thing. But this is this very general name of an incidence algebra. So the set of functions which we consider are functions from P2, so functions defined on pairs of arguments, where the first argument is less or equal than the second, let's say complex numbers, with pointwise addition. So this means the sum of the functions applied at some arguments is just the sum of the functions applied at these arguments, the usual definition. Okay, but for the multiplication we don't do it pointwise, but there we use the convolution. Convolution really has much more structure about the poset. Okay, so we have pointwise addition and convolution is star. Of course, you should check that this fits together. There's this distributive law which you have for those operations. That's okay, you should check this. So this set of functions, so the function of those two variables together as these operations, is usually called the incidence algebra of P. Incidence algebra of P. Okay, so I mean this is a very general notion, and it's not really using much structure. I mean, the poset is very general. It's just a partial order which you can have in many situations. No? So the power of this is not that it's very deep and using complicated structure, but that it's actually so general and really tells you exactly what is relevant in many situations. Because you have many situations in very different settings in mathematics where you have such a poset, and actually such questions here are important. Good. Okay, what is now particularly important for us is essentially the question whether there is an inverse of the zeta function. Okay, because what are we really interested in? I mean, our case of this convolution is that we have two functions, one variable functions, which are related by summing over the whole poset. And this means that we are taking a convolution with the zeta function. But this is the relation between how moments are given in terms of cumulants. That was always how we saw. We got formulas that the moments are given in terms of sums over cumulants. No? But of course the cumulants, we should define the cumulants, which means we should solve this equation for the cumulants in terms of the moments. No? And abstractly, the moments given in terms of cumulants is the convolution with the zeta function. So solving this is the question whether there is an inverse function which gives us the other way around. The inverse of this is called the Moebius function. So what we are asking here is the question whether we have we have this inverse, and it turned out we have this for all posets, and it's usually called the Moebius function. And this is a very general setting. Very often, in many different contexts, you have this relation between functions in one way, and then you want to resolve it the other way. This means you have to involve the Moebius function. And the Moebius function is the object for your given lattice and or for your given poset. Okay, good. So our main interest is in a special case where I have one variable function which are related by the convolution is the zeta function. No? You should think of this, those are the moments and those are the cumulants. No? That was somehow the type of formulas which we had. No? But of course, I mean, we didn't really define the cumulants. I mean, they should be defined by this formula, but this means we should express G somehow as a factor in terms of F, no? Which means we should bring this zeta on the other side as the inverse, and that's a question whether there exists an inverse. Maybe let me write this here. Maybe let us check what this really means. No? So I mean, this here means F of sigma is given by our definition of the convolution. I'm summing over elements in my poset which are less or equal than sigma. And then I take G of tau, and then I take zeta of tau to sigma of the rest. Okay, so that's a general form of our convolution, but the zeta function is always 1. No? For any tau, this is equal to 1. So you see what we are doing here is we are just summing over G of tau, where tau is our poset, and tau is less or equal than sigma. This is really the type of formulas which we had between moments and cumulants. Okay, so this abstract formal language, this just means that they are related by taking the convolution as a zeta function. And now we want to define the cumulants or solve this, and this means we should find inverse of the zeta function. So F corresponds to moments, and G corresponds to what we are going to call cumulants, or free cumulants. But the whole thing also works in the classical setting. Of course, then the poset is given by all partitions. Now, for all partitions, you have the same partial order. Good. But so the main question is, in order to define cumulants in terms of moments, we have essentially to solve this equation for G in terms of n. So we should solve the relation F is the convolution of G with zeta. We should solve this for G. Good. Okay, this of course means we should have an inverse of this, and it turns out in every poset such an inverse exists. It's uniquely determined, and it is called a Moebius function. Okay, so that's the next main proposition in this very general context, that you have the existence. And of course, the inverse of this has nothing to do with F and G. It's just the inverse of this in this convolution setting. So I mean, these here are just essentially, I mean, these are a system of linear equations, so it's just, I should just see that I was able to solve them. Good, so let me correct the statement in the next proposition and then we're proving it. The proposition here is that actually the question is whether, not every function has an inverse with respect to this convolution. No? Okay, but the zeta function has an inverse. So the zeta function is inverted with respect to our convolution. So this means that exists a function two-variable function, which we call mu. So this is an element in the incidence algebra. So it's a function on P2. This function is usually called the Moebius function. And the defining property that it is the inverse of zeta, of course, means that if I take convolution of mu is the zeta function in any order, zeta convolved with mu, or mu convolved with zeta, I always get delta. Delta is the unit, the one in my convolution algebra. Okay, the proof is not very hard. You just must think a little bit about what those equations mean. That they give you a kind of recursive way of defining them. Or they are a system of equations which you really can solve. Okay, and so in principle we have two relations which mu should satisfy. So it's a right inverse and it's a left inverse of zeta. And so let us take one of them, use this for defining the Moebius function, and then think a little bit that the other equation is then automatic. Okay, so let us take the second relation. So namely this one, that this is equal to delta. So what does this really mean? So mu convolved is the zeta function. So just write down. Okay, so mu convolved is the zeta function should be the delta function of d and sigma, which of course takes just all the values 0 or 1, depending on whether pi is equal to sigma or pi is strictly less than sigma. Okay, but here this, what is this? By definition of the convolution, this is summing over all tau, which are greater or equal than the first element, greater than pi, and less or equal than the second. So elements which are interval from pi to sigma, then we apply mu to the first part of this interval. So we have mu of pi tau, and we apply zeta to the second part. So we have zeta of tau to sigma. Okay, but the zeta function of course is 1 everywhere. So this is just 1. And what I have here is just this summation. So it's the sum over tau in the interval from pi to sigma, just summing of mu pi tau. Okay, good. And so we just have to see. So that's actually the equation. Huh? So that the convolution of mu is zeta function is delta means that for any pi and any sigma, this sum here over the taus has to be equal to 1 or 0, depending on whether pi is equal to 0, sigma, or pi is equal less. Yes. And actually, this is now an equation which one can solve by recursion. So this can be solved recursively in the following way. First we should look, essentially recursively means I want the value of pi to sigma, and so this means this should only depend on the interval from pi to sigma. And recursively I'm filling essentially the interval from pi to sigma. So I start by the interval I start at the beginning, so I should look on pi comma pi, and then I'm getting bigger and bigger ones. And for if pi is equal to sigma, then this equation tells me directly what mu of pi comma pi should be. Yeah, so namely if I consider this equation for the special case where the two arguments are the same, so where pi is equal to sigma, then of course on the right hand side I get 1, and this sum here, I'm summing over tau, which are between pi and pi, because sigma is now pi. This means I'm summing just over tau. No? This means I have only one term here, which is mu of pi comma pi, because tau is then pi, and this guy must be equal to 1. Okay, so this equation is very trivial, because the equation just says mu of pi comma pi is equal to 1. Okay, so that's easy. Starting condition or recursion. So in particular, we have that mu of pi comma pi, where both arguments are the same. This is equal to 1. And this is true for all pi in my poset. Okay, now if I have a general sigma, which is not equal to pi, then this, and I want to know what is mu of pi comma sigma, then I'm going to this equation. I have this equation, pi is not equal to sigma, so the final result is 0, and I'm summing here over all the tau between pi and sigma, so in particular I'm also including the term that tau is equal to sigma. So I'm getting here also the term mu of pi comma sigma, and I got to get other terms which essentially recursively I already know. So this equation here tells me that mu of pi comma sigma plus the sum here over the taus, where tau is not equal to sigma, and this is equal to 0, or the other way around, and this term is equal to minus the sum q pi is less than equal to tau, and tau is strictly less than sigma. Here I'm taking mu pi comma tau. Okay, and now by reduction, or recursively, I can assume that I already know those guys. Because I mean, I'm here in interval from pi to sigma, and in this interval, I mean, if I know all the values of mu of pi comma tau, for all the taus which I like in this interval, then I can calculate this for sigma. Okay. And I know the point of the starting interval, so of pi comma pi. Okay, so I start, I'm doing mu of pi comma pi is equal to 1, and then I take the element, the next element in this interval, so this means an element which is bigger than pi, but where there is no other element in between, and then this tells me what is the value of this. And then I can take another element and go on until I reach the end of this interval. So this is an inductive or recursive way of calculating this Moebius function. Okay. And so this, yeah, and this I can use this as a definition. Okay, so I can solve it in this recursive way. And this means what I'm getting here is, of course, the solution of this equation. Because I have used this equation, I have solved recursively this equation. Now the only question is, why is the other relation also satisfied? And for this, okay, I mean, maybe the best way to see this is actually that what we are doing here is actually matrix multiplication. And if for matrices you have a left inverse, it's automatically a right inverse, and the other way around. So maybe a bit more concise on this, because this might also make the structure of all these things a little bit clearer. So note that we can also view the definition of our convolution. Convolution F convolved with G as a matrix multiplication. Of which matrices, of the matrices which contain the value of our functions. So namely, let me write, I mean my poset is just a number of elements, so let me just number the elements. Let's say if there are elements from P1 to PR. So I'm just writing P, my poset, consists of element P1 up to PR. And then, of course, I have functions of two variables. Then, of course, I evaluate my function at all pairs of those guys, and I just put them into a matrix. Only the matrix, I should have a full matrix where I also have values, Pi and Pj, and maybe Pi and Pj are not comparable, but then I just define the function as 0. So this definition that my function should only be defined on those pairs. Of course, I can also say my function is defined everywhere on all pairs, and for pairs for which it is not true that chi is less or equal to sigma, I just say the function is 0. This is again compatible with this. Because in this definition, the value of the function on such values doesn't play any role. And of course, this formula is okay because if I have here something which is not compatible, then where pi is not comparable to sigma, then of course there is no sum. Then this formula also tells me that the value should be 0. Okay. But then I can say I have functions which are defined in all pairs of pi's, and then I can put them into a matrix. Then I can identify my function as a matrix. So I put, let's say, my function f. I identify this with a matrix which I call f hat. So this is a R by R matrix, where the ij entry is just f evaluated in pi I and pi j. Okay, I'm doing of course the same for the g and let's say h. I'm just taking here function g and h. So if I have functions f, g, and h of two variables, I associate those matrices to them. And maybe important to note, put functions on variables where the first variable is not less or equal than the second. We just say it is 0. It's not less or equal than j. Okay. Of course, for matrices, the entry should be defined for all choices of I and j, not only for the ones for which I is less or equal than j. Good, but in this matrix language, then, the fact that the function h is the convolution of f with g, this is equivalent that the corresponding matrix is just multiplied. So this is the same as saying that the matrix corresponding to h is the matrix corresponding to f multiplied is the matrix corresponding to g, and this is just ordinary matrix multiplication. Because essentially that's what you're seeing. This is a matrix indexed by pi and sigma. Okay, and then what you're doing is pi is here, sigma is here, and you're summing over this index, which is exactly matrix multiplication. Okay, and the poset structure you don't see it here, but maybe if you can strengthen this a little bit by essentially ordering your pairs, the I and the j, in such a form corresponding to the order of the pi's, and then you will see that actually the functions which you have are triangular matrices. And then the question about the inverse is also something which becomes clearer. Triangular matrix you can invert exactly if on the diagonal you have elements which are different from 0. But the zeta function is 1 on the diagonal. So this will also give you another proof for doing this here, this matrix language. Okay. But for this you have to see that actually you should order those guys in such a way that it respects the partial order of pi. Of course you can do this. And then those matrices here will actually be triangular matrices. Good. Okay, but I only want to use it. I don't care about the order because I already have shown you that I can solve one of the two equations. But now in this matrix language, so this tells me that I have found left or one inverse of the matrix corresponding to the zeta function. Okay, but for matrices, if I have a left inverse, I have automatically a right inverse. And this means it also satisfies the other equation. In infinite dimensions, of course.
I just have a question. Shouldn't one also prove that the matrix inverse has zeros where it should have zeros? Because otherwise, well, what we have found by that construction doesn't show us the whole matrix. So in the pairs which are not the correct order, then we don't know what to put there because it doesn't matter for the multiplication.
Yeah, I mean, there my entries are all 0. Okay, so you should think. But actually, I mean, I'm just. Well, I mean, you just have to see I mean, if I associate to my functions those matrices, then the matrix multiplication really respects this association and it also respects the zeros. So this means if you start with 2 matrices corresponding to those functions and you multiply them in the matrix way, then as you say, you get zeros at the points where they are not comparable. Okay, but that's what the matrix multiplication does.
Yes, but maybe we should also prove that the inverse also has the zeros where...
No, I don't. Because I know if I have the inverse, this I mean, I have a function for which the multiplication gives what it gives, or what it should give, and then I know that the corresponding function of my things here has exactly the property which I want. I mean, I'm not talking directly about the inverse, I'm just talking about the equations which tell me that something is the inverse. And these equations tell me that also in this incidence algebra I have the inverse. So I mean, let me do the argument, I mean, just writing down what I just said about why the other equation is satisfied. So up to now I have not really, I mean, I have proved to you that I have the inverse, or I have something which satisfies this equation here. Okay, so and of course, I mean, this matrix, of course, the matrix corresponding to the delta function is, of course, the identity matrix. So delta hat, the identity matrix. And so this means the relation which we have proved, so namely this equation. So this gives the same relation for the corresponding matrices. So namely, what we have proved is this that mu hat multiplied with the zeta function matrix gives delta hat, but this is the identity matrix. So this tells me that this matrix here is the inverse of this matrix. Okay, but now for matrices, if I have the right inverse of a matrix, this is automatically a left inverse. Finite dimensions. Okay, so this means this here, this implies automatically that also the other way around, zeta hat times mu hat is equal to delta hat. Okay, but then this gives me exactly this equation here. So this tells me that also zeta involved with mu is equal to delta. Of course, it's important here that I have infinite dimensions. Of course, in infinite dimensions it's not true that the left inverse is the right inverse, but infinite dimensions for matrices, because I have a determinant. This is the case. Because if A times B is the identity matrix, then automatically B times A is also the identity matrix. Because having an inverse can apply determinant to this equation. Good. Okay, so this tells me that, yeah, I really have an inverse of the zeta function, and this means I can also invert the relation. If I have f is g converged with the zeta function, I apply the Moebius function to this, and then I get it the other way around. And so this means those two things are equivalent, and that usually goes under the name of Moebius inversion. So I have in the poset, I have this very general Moebius inversion, which tells me that I can invert such relations between two functions. So that is how the corollary. This is a crucial thing for us. And of course, I mean, this is called Moebius function because it was introduced by Moebius, but in a very different context. I mean, this comes from number theory. In number theory, the poset, I mean, is given by natural numbers, and the order relation is given whether one is a divisor of another number. Also, for a pair of numbers, the question is whether one number divides the other, then you say it's less or equal. So this means you're essentially having functions, one functions which you define by summing over the divisors of your given number and taking the other function, and then of course you want to invert this, and this is the classical Moebius function in number theory. Okay, but here, I mean, so this here is a much more general. So this relation is too much more general. Any poset. Now, it's Moebius inversion. Okay, so let P be our favorite poset. P be finite poset. Of course, the natural numbers are not finite, but they are locally finite, which means if you are summing over things, then it's only, each number only have a finite number of divisors. No? So, I mean, then all those things are still true. Okay, so but for us, all our posets are finite. Okay, and then the statement is that there exists a function, a Moebius function, but this is also uniquely determined. The relations which we wrote down, I mean the inverse is uniquely determined, is uniquely determined Moebius function. So this is denoted by mu. This is an element in the incidence algebra by poset, so it's a function of the two variables. And what is the crucial property of this function? So it is that it is the inverse of the zeta function, and I want to write it down in the relation between two one-variable functions. And essentially it says that if one function is the convolution of the zeta function of the other, then I can invert this. The other is then the convolution of the first with the Moebius function. So such for any, we take one-variable functions. You could also relate the convolution of two-variable functions, but in our case, our functions are one-variable functions. So it's functions from P to C. So the following statements are equivalent. So the first one, the function f is the function g converged with the zeta function. Write down explicitly again what this means, that I get f at the element sigma by summing over all pi in my poset, which are less or equal than sigma, and I'm summing over g of pi. So I'm summing over all pi's which are less than sigma. Okay, this is equivalent. So if I have two functions where one is expressed in terms of the other in this way, this can be reversed. Equivalent to the fact that g is actually the convolution of the function f with the Moebius function. I mean, of course it is clear. If mu is the inverse of the Moebius function, I just multiply this equation with mu on both sides, then zeta goes away, and here I get f converged with mu. So this is the corollary of the existence that mu is the inverse of the zeta function with respect to this convolution. Okay, and this here means explicitly g of sigma is given by summing over my poset, again summing over all pi, which are less or equal than sigma, and I take here f of pi, like here, but now I also have the Moebius function. And here I don't have the zeta function, but this is 1 always, but here I need the Moebius function. I have here mu of pi, comma sigma. And of course this means, in order to understand things, I better should have try to understand the Moebius function. Of course each poset has its Moebius function. And of course the structure is the same for all posets, but the actual value of the Moebius function, that's really what tells me something about the poset. The values of the Moebius function depend on the chosen poset. Good. Okay, so that's the general structure. And of course the point here of this inversion is, I mean, I have here a relation between two functions, but this inversion doesn't really rely on the specific value of the functions. I mean, this mu here only depends on the poset, not on the functions f and g. So for all f and g, which are related like this, I get the inverse version like this. And here is no specific information which involves the f or g. Good. Okay, so this is general one, cumulants and moments. Yeah, but now of course our functions which we had had some more structure. So actually they were of a multiplicative type. So namely we had this formula, the moments are given by summing over our non-crossing partitions, but then actually the term which we had there for partition was now a product of cumulants according to the block structure of our partition. So I mean we are now not looking on any arbitrary function on our poset. So our poset of course are non-crossing partitions. But we are not really interested in the incidence algebra in general, because those would just be functions on our non-crossing partitions. But we are interested in very specific functions which somehow respect in a multiplicative way the structure of the non-crossing partitions, namely the block structure. So what we are now dealing with are multiplicative functions. So we have to understand this a little bit better. G of pi, but this G of pi was actually a product of contributions coming from the blocks of pi. So those have quite special structure, namely kind of multiplicative structure. Multiplicative structure. Namely, what I have is a factorization according to the blocks of it. Okay, and if I have this for the cumulants, I mean it will also be the same for the moments. And so what we are really dealing with will be multiplicative functions. And of course this is something special for our poset. Of course, I mean this depends on the fact that elements of our poset are really given by blocks, and then I can make a decomposition of the function into blocks. On the general poset, there is no notion like a multiplicative function. Okay, but here we have more, our non-crossing partitions have more structure, which we can use. Okay, and actually, so the formulas which we had were more or less formulas for one variable, where we look at the moment of one variable, and we also had cumulants of one variable, and only at the end I look on joint ones. And of course we would like to have this notion of cumulants very general. So namely also for the joint moments and also joint cumulants. Okay. So So what we need are actually not just functions which take on complex numbers, which would be the moments, but we would like to have objects which are more like joint moments. And those we consider as multilinear functions. So what we really have now, the following definition, which is 3.7, but again, it seems okay. Skipping, the problem should be 3.8 now. The definition, which is the definition of a multiplicative family of functionals. Okay, so yeah, we are also going back a little bit to our general situation. We have objects defined on algebras, and there we have our moments, and so that A here in the algebra, and then you assume we are given the sequence of multilinear functionals of A, or given the sequence. Say rho n for all n, 1. And I assume that those are multilinear functionals from A. So this means each row n, and the n indicates how many arguments those guys have. So they have different number of arguments. Row n has n arguments, so it's a mapping from an to c. Functional means it's a mapping to c, so it should be a mapping, and it's multilinear. So if it has n arguments, it should be linear in each of its arguments. So this mapping sends in tuple an, a1 up to an to row n applied to a1 up to an. Okay, those row n, I assume they are linear in each of its arguments. So this one should be linear. Okay, now I extend this. So I have here a mapping. I mean, those guys you should think of as being the mappings corresponding to the blocks. So if a block has n elements, I know what I have. I have a moment or I have a cumulant, but in general setting, I mean, I want several variables at the same time. So actually I have here those functionals defined also in my algebra. Okay, so the row n's are the guys for the blocks. For a block of n elements, I have row n, but now I want to extend this in a multiplicative way to partitions. Okay, and then I should take a product of those guys corresponding to the block structure. Okay, so if I have this, then we extend this family of multilinear functionals. And now, I mean, I want to have such a guy for any non-crossing partition. And actually, I mean, the size can also vary. So I start not to look on non-crossing partitions of just 5 elements or just of 8 elements, but I just take them all together, because that was also what was happening essentially in my formula, that I take cumulants of smaller sizes, which essentially correspond to smaller partition lattices. Okay, so I want to have a row pi for all n greater or equal to 1, and pi is a non-crossing partition of n elements, but n can be arbitrary, and I define this. So I extend, so I'm given the row n, but I extend this to a row pi, and the definition of the row pi is the formulas which we always had in the last chapter, that I should take a product of contributions according to the block structure of pi. And for the blocks of pi, it only is important, essentially, it's important how many elements it has. And then I take a product of the blocks. But now, of course, I mean, I have multilinear functionals, so I also have arguments, which I should distribute according to the block structure. Okay, so formula. Yeah? formulas. Setting. So, okay, so what I have to define? So row of pi. Pi is a non-crossing partition of n elements, then row pi should be a multilinear functional of n arguments. So it goes from A to C. So like the row n, it's a multilinear functional, which means I have n arguments coming from A, and I get something, row pi, of those arguments in 1 up to an. Okay, so what's the definition? So multilinear functionals, okay, those guys, and then by the formula, so I should tell you what is row pi of the arguments a1 up to an. Okay, this is given by a product of the row n's, which I have, according to the block structure. So I take the product over the blocks of pi, and for each block I get a contribution. And what is the contribution? I take the row with the number, where the subindex here is the number of elements in the block, so it's row, the number of blocks in V, and then somehow I also have to put arguments there, and this needs so many arguments as I have elements in V, and of course the arguments I should take somehow from those, and I think it's clear which ones I take, namely those which are essentially corresponding to this block. So I mean, I have here a partition of n elements, so you can say I essentially have a partition of those random, of those guys here, a1 up to an, and each block of them connects some of them. And those are the elements which I'm putting here in this row. So I denote this, you don't need to have 1 up to an restricted to this block B. So in this, you write it down more formally what this is. So if my block consists of elements I1 up to IS, so this block has S elements, and usually if I'm writing down a block, I always mean that those elements are ordered. Because I can of course make a choice, but usually I assume I1 is less than 2, and so on, up to IS. And then with this here, so this would then be row, the number of elements in this block is S, and I have here my n variables, A1 up to AN, but this means only S of them should be taken as arguments here, and I take of course the ones which correspond to the position which are given by my block. So I take here a row of A1, A2, and so on up to AIS. Okay, so this is the same formula as we had before for the connection between moments and cumulants, but there we essentially only have numbers, which we multiplied here. But now, of course, we have this more general functions. Okay, and so I mean, this is just a definition. So if I'm given multilinear functionals for each n, I can extend this in a kind of multiplicative way to multilinear functionals which are indexed by non-crossing partitions. Okay, and then all this family of all those row pi, we call now a multiplicative family of functionals given by the row n. So this collection of all the row pi's, where for any n, for any pi, an nc of n, so this is called a multiplicative family of functionals on, where, I mean, actually it's now not just defined on nc of n for fixed n, but it's defined on nc of n for any. So it's essentially those guys are living on the union of all nc n. And for this I just wrote nc, which is just the union of all nc n, that will be union over all n greater or equal to 1. Okay, and of course this family, of course, needs some input, and the input are those guys here, those row n. So we say this is a multiplicative family of such functionals on nc and it's determined by the row n greater than equal to 1. So essentially we have a sequence of row n's of linear functionals, and this gives us this multiplicative family where I have a family which is indexed by non-crossing partitions. And the definition is in this multiplicative way, I'm just multiplying according to the block structure. Okay, maybe let me make a few examples just to make clear that we understand this definition. Abstract, but it's really what we need, and it's the most general thing. It will give us very soon a definition of our free cumulants. Okay, so this is this one. Let's have some examples because they might be anyhow. Okay, so the examples, of course, first of all, the row n's, of course, are special cases of the row pi. Namely, if I just take the maximal elements in my underlying NCN, then of course in this product I only have one term. So if pi is the maximal element, then it has only one block, and then essentially I get to the row n. So I really have an extension here. So namely the row n is just the row of the maximal element 1n. So this means the row indexed by this partition which has only one block of arguments a1 up to an. This is now really the row n of those arguments. Because I mean this block takes all those arguments together. A1 up to a. Okay, but now if I have a let us now consider maybe more interesting example. So let's say pi is, let's say the partition 110, 259, 4, 6, and 7, 8. So this is a non-crossing partition, 10 elements, and of course it's best to draw those guys. And maybe let me also write down my arguments, which I want to put into this guy. So those are a1 up to a10, 5, 6, 7, 8, 9, 10. And I have here the partition. So 3 is connected with 4, 6 is a singleton, 7 is connected to 8, 2, 5, and 9 are connected, and 1, 10 are connected. So this is my non-crossing partition. And so for this I have a corresponding row pi, and I have 10 arguments, a1 up to a10. Okay, but what is this now? It's just now the product of rows corresponding to the block. And so I have here, let's say, I have here the block containing 1 and 10. So this is a block containing 2 elements, and of course this takes a1 and a10. As argument. Then I have a block of 3 elements, 2, 5, and 9. And this takes as arguments the corresponding A2, A5, and A9. A2, A5, A9. Then I have a block having only one element, so I get the row of row 1, which needs one argument, and it gets A6. Then I have another block of 2 elements. I get the row 2 of the corresponding arguments A7 and A8. Okay, so I hope it's clear. So I'm just taking the product of the blocks, but now in addition to just having numbers here, I have arguments, but then I also distribute them according to the block structure. So this means each argument on this side appears exactly once. I have all the arguments which I have here, they all show up here. And they show up exactly once, which means, of course, those guys are also multilinear functionals. Because, I mean, each A appears exactly once here on this side, and it appears in one row, which is multilinear in this argument. Okay, so, that's the definition of this multiplicative family. And now I mean we are ready essentially to define the free cumulants. So I'm starting with the moments. I must make out of the moments a multiplicative family, and I can take then the convolution of this with the Moebius function, and then I get the free cumulant function. Good, but I think I will do this next time.